Hello everybody, I'm here with a very simple video of a frame that I want to show you how you can determine forces that are developed in different pin connections here. So first of all, frame is defined as structures that are structure which will support the applied loads. Unlike trusses, that each member of a truss is a straight two-force member, frames are made of at least one multi-force member. Multi-force member means that you have at least two forces or two forces, at least three forces or two forces and a couple. Okay, and frames are typically stationary, so they are fixed. So here, as you could see, we have basically three members, member A, B, and let me call this the middle of this pulley D, and then member B, C. Now, of course, this cable which goes around, and we are applying a 400 Newton tension. So let's say the objective is to determine the components of reaction developed in each pin here. So typically when you start to look at a frame problem, you should draw the free body diagram of the entire frame before you take it apart. Okay? And then once you do that, you should be able to figure out all the external reactions, or if you cannot find all of them, maybe you can find just one or two of them. In this case, it turns out that if we draw a free body diagram of the entire frame, so you know we have a pin here at A, so we have AX, AY. Again, I don't know about the direction of these. Same thing here, CX and CY. And keep in mind that we also have the same 400 Newton tension acting here in this segment of the cord. So notice that you have four unknowns here. So you won't be able to figure out all the unknowns. But since point A and C vertically are lined up, if, for example, I go ahead and take moment about A, right, say counterclockwise is positive, notice that C bypasses through A, so it doesn't have any moment about A. That leaves moment of Cx, which would be Cx times 1.5 about A, going counterclockwise. Then, by the way, the radius of this pulley is given to be 0.2. So we have a 400 times 0.2 going negative, and also 400 coming from this guy times 3.8. Be careful, it's not 4. You got to take the 0.2 out of that. So overall, I think we get a Cx of, so basically it becomes 1600, if I'm not wrong, divided by 1.5, which is about 1060, if I round it, about 1067. Okay? 1067, and I put my decimal point in the wrong place, so let me just clean this up for you. 1067 newtons. Okay, now if Cx, and the direction of Cx is right, because I ended up getting positive, therefore Ax has to, if I now sum forces in the x equals 0, right? If I sum forces in the x equals 0, looking again at the entire frame, right? I have Ax plus Cx, which is 1067, plus this 400, right? And notice that the Ax should be then minus 1467, roughly, which means that Ax should point the other way. So the correct direction of x, it should switch and be in this direction then. All right, but we cannot find either Cy or Ay, because all we can say is that Cy plus Ay must be equal 400, basically balancing the forces in the y direction. So you see, now we have to go and start drawing the free body diagram of individual members. So for example, let me just show you what happens to the pulley. We can actually keep the pulley on member A, B, D, or separate it. You see how, if you look at this pulley by itself, you have a 400 tension in the cable. At D, you have a pin, so you're going to have a dx and a dy. Just by inspection, dx must be equal to 400, like that, and dy should be equal to what? 400 up. But now, if you come and draw the free body diagram of your member A, B, D, notice that you already know that AX is what? 1, 4, 6, 7. Have no idea what AY should be. We might be wrong about the direction. Let's look at this point, point D. You see, these are the forces that the middle of the, these are the forces that actually the pulley, or this point on the bar rather, exerts on the pulley. The forces that the pulley, the midpoint of the pulley, point E, exerts on this end of the bar is going to be in the opposite direction. So you see this dx acting to the left should be 400 to the right, and then similarly the 400 pointing up should be 400 down. Then that brings us to this question: what is happening at B? Well, B is just bx by is a pin, right? So I'll just go ahead and I put bx and by. Even though you'll see in a minute that actually this member BC is a two-force member actually, and we should always look for those two-force members. Not so important in this particular problem. I'll just come back and I show you that BC actually is a two-force member. So look guys, if you just take a moment about B, by inspection you could see that since everything is lined up along this horizontal line, only AY and this 400 that have moment. So AY times 2 and then 400 times 2. So AY has to switch direction and it's going to be 400 negative, which means AY should be 400 down. So its direction has to switch. If AY now is 400 down, right? What should be BY? You have a 400 and a 400 going down. Therefore, BY then must be equal to 800, right? Balancing the forces. So the direction of BY is correct. 800 like that. These are, by the way, in newtons all. And then by balancing forces, you see BX should be what? BX should be 1067 to the right. Okay? So you see we got everything. So now you can go back and now that you have AY, for example, and you know AY is pointing 400 down, so you have a 400 down here and a 400 down here, so CY must be 800 up. See that? And what I was saying, guys, is that BC actually is what we call a two-force member. It's not a straight two-force member, but is like in the form of a bracket. You see how here I have CX equal, I earlier found CX to be 1067 and just got CY to be 800 up. You see how BX and BY acting on this member are in these two directions shown. But when I show it on the member itself, member BC, you see how BY is 800 up, is going to be 800 down here, that BY. And similarly, BX is 1067, which is to the right, it should be to the left. And you see how they're balancing exactly these forces here. In fact, you could actually show this as one force, one resultant force acting like that. This would be the force in member, if you want to call it BC or CB. Okay? Exactly like that, which you could actually find the resultant of it if you want. It's the square root of 1067 squared plus 800 squared. So remember, this was a very rather simple frame example. And hopefully I'll come up with more examples of a frame. Soon I will show you an example of a machine, which would be example of a plier. So as always, if you like these videos, please subscribe, and you'll see more example of these hopefully every week. Thanks for watching.